In the first problem, we have an isolated vessel divided into two equal volumes of 10 liters each. One chamber consists of 40 mole% methane and 60 mole% helium at a pressure of 3 bars, while the other one consists of pure methane at a pressure of 1 bar. Both chambers are 300 K, and you're asked for this situation to evaluate the enthalpy change that occurs when the partition between the chambers is removed and the gas is mixed. And you're told to assume ideal gas behavior. So here's a diagram of the situation, and we can right away calculate, since these are ideal gases, that the final pressure is just 2 bar. Now we have a number of little things to do here. We can imagine before we get started what we would need to do. And that is to, first of all, adjust the pressures in both chambers to the final pressure, which is 2 bar, and calculate the enthalpy change associated with that. Then we would need to demix system 1 to pure components. And now we have pure components both at, I should say, at the conditions of the final mixture so that we can mix them. So it's a combination of these steps, and then it's just keeping track of the amounts that are involved. So I calculated first the total moles of methane and hydrogen, there they are, in the system. Then I can calculate the final mole fractions for methane, and then the other one, of course, is going to be helium. Now I have all of the, and then the total moles in each of the chambers, which I'm calling 1 and 2 here, so I can calculate them. And now I have all the pieces that I need to put together to calculate those 4 pieces that lead to the total entropy change. And here it is, delta S in total is first adjusting the contents of 1 to the final pressure, adjusting the contents of chamber 2 to the final pressure, then the third step would be to demix the contents of chamber 1 to pure components, and then lastly mix all the pure components. So executing that is, it looks like here's the first one, second one, and I've just left R in there because R is going to multiply all of these numbers and go on through it like that, just with the formulas that we have, remembering that mixing and demixing for entropies are minus R times the summation of these Y log Y terms. So here it all is, and it ends up, for me anyway, as 4.182 joules per K when I add it all up and put in the gas constant R, 8.314 in terms of joules per mole K. Any question about this one? Important thing is that you know how to put all these pieces together. Who knows about arithmetic? There's a lot of it in here. I hope I haven't made a mistake. Okay, let's go on to the really important number 2 problem, which is one of the most important systems that we find, water and sulfuric acid, and solutions of these two materials at 18C have a heat of mixing, which is given by this expression. This has been obtained experimentally doing calorimetric measurements. And you're asked from this information to derive expressions and plot the partial molar enthalpies for the water and sulfuric acid as a function of the mole fraction of water, taking reference enthalpies of the pure components here to be equal to 0. Since we're dealing with enthalpic quantities, and we know we have to reckon if we're going to get a number to put on those, we need to pick a reference state. And a convenient one to choose is to just set these molar enthalpies of the pure components equal to 0 respectively. So as always, we can write down the molar quantity here of interest. It would be the molar enthalpy of the solution is going to be the corresponding parts of the pure component plus whatever the molar heat of mixing is. This is essentially by definition. These are both set equal to 0. And so we have a systematic procedure for doing this. When our objective is to calculate partial molar quantities, then I think it's good to not try to take any shortcuts and just go through and do this. And the first thing is to put the mole fractions, in this case the x's, in terms of n's. So x1 is n1 over n, x2 is n2 over n, as I've shown here. You just do that, and then multiply through by n. And when you do that, you have an expression for the extensive enthalpy, which for our case now looks like this. And then you can implement the definitions to calculate the partial molar enthalpies. So the definition here of the partial molar enthalpy for component 1 is the derivative of this extensive H with respect to N1 at constant intensive state, Cp and N2. So here's just a matter of doing this differentiation of this expression. And once that's been done, it's convenient to go back and put it in terms of mole fractions rather than in mole numbers. And I left it with both x1 and x2 in the expression. You could have put it all in terms of x1. There's many ways you can write this final result. You could have put it all in terms of one fraction if you wanted. So unless you left it like this, it's going to be a little bit hard to compare answers here directly. And we do exactly the same thing for H2. That is, we go back to this expression and now differentiate with respect to N2 at constant N1 and Tp. And anyway, end up with this expression. So now we're ready to plot them, and it's convenient to make a spreadsheet for this. So I can write down a series of x1 values and calculate each of the partial molar quantities, enthalpies, for those mole fractions, and this mole fraction of 1, so this is the way the final plot looks. You're asked then here to use the results to determine the heat absorbed or evolved when 100 grams of solution of 71% sulfuric acid is diluted with 50 grams of pure water. So we've got just a little bit of stoichiometric calculations to do to put this in terms of mole fractions. But what I've got here is the solution 1, 38% water, 78% sulfuric acid, and here's my pure water. I'm going to mix those to get a final solution. So I can just do the stoichiometry here and get that these initial mole fractions, x1 is 0.7 in this initial solution, and the final ones, keeping track of everything, I get ultimately 0.861 for the mole fraction of water and 0.139, then of course for the mole fraction of sulfuric acid. So then the important thing is to realize how simple it is to calculate the enthalpy change for the mixing of any mixtures like this for which we have knowledge of partial molar quantities. So here's delta H is going to be the extensive enthalpy here of the final solution, which I've called solution 2, minus the total extensive enthalpy for system 1, minus the enthalpy for pure water, but of course we know that's something that's just 0. So now I can write out these extensive enthalpies for the solutions in terms of the partial molar quantities and the given mole numbers, and here it is written all out. Now I can go back to the spreadsheet and I can stick in the exact number here, because once I've got it, let's put it in another line and get the exact number from the formulas that are already keyed in there, and calculate all of these numbers, put them all together, and end up with minus 3.28 kilojoules. And it's important that we recognize that there's a minus there, which means that heat is evolved. So the enthalpy change is always defined as the heat absorbed. So if the heat absorbed is negative, it means that heat was evolved. And you know that very well. Mixing sulfuric acid and water is highly exothermic. In fact, it's dangerous. Any question about this problem? Okay, next we've got mercury barometers filled and calibrated in a repair shop. The mercury is stored in a small room that has no ventilation. The mercury spill occurs in the storeroom and is not completely cleaned up. What is the maximum mercury concentration that can be reached in the storeroom if the temperature is 20 degrees C or if it's 30 degrees C? Is either level acceptable for worker exposure? The present federal standard, the OSHA permissible exposure limit, PEL, for mercury in air is a maximum allowable value of 0.1 milligrams of mercury per cubic meter of the gas, of air. Okay, so we got information on the vapor pressure of mercury here in the form of Antoine's equation. Now, this is slightly different than the forms you've seen before, but this is kind of on purpose for you to realize that, yes, you can find these Antoine equations in different formats. So we get the common logarithm of the vapor pressure given in millimeters of mercury is given by this expression, and here the temperature is in degrees C. So the approach to this is a very simple problem. This is actually a 310 type problem. So what you do here is you can calculate the vapor pressures, or the partial pressures of the mercury from the knowledge of Antoine's equation at the two temperatures that are of interest here, and compare them to the OSHA PEL values. Or you could take the OSHA Pell values and convert them into mole fraction and make the comparison. So you can do your unit conversions either way, but that's all it amounts to, are unit conversions. So what I decided to do was take the Pell requirements in terms of milligrams per cubic meters and convert those over into mole fractions. And actually into, yeah, I did it in terms of mole fractions, and then we'll compare them with what the Pell values would be. I mean, compare them with what the actual values would be. So the Pell values at 20 and 30 degrees C I get just by doing this, essentially, unit conversion. I get 1.2 times 10 to the minus 8 at 20 degrees C and 1.24 times 10 to the minus 8 at 30 degrees C. Now the actual mole fractions are computed as noticing this, that the mole fraction of the mercury is going to be the partial pressure divided by the total pressure, which is 1 atmosphere or 760 millimeters of mercury. It's indicated here. So I can do that calculation, and I see that what I actually end up with is 1.7 times 10 to the minus 6 for my mole fraction at 20 degrees C, and at 30 degrees C I get 3.93 times 10 to the minus 6. And I will note by comparison here that both are more than 100 times the permissible exposure limit. So we've got a problem in that lab. Better ventilate that quickly or get out of there. And this is kind of a PSA type problem that they want us to expose, so people should be aware that mercury is kind of a dangerous thing, and you want to be very careful of spills and having it in the atmosphere. So
do you remember?
hope that point is taken.
0.1.
Milligram per cubic. Yes.
Okay. Next, let's look at calculating the fugacity of liquid ammonia at a temperature of 0 C and a very high pressure under 150 bar. Second variable coefficient for ammonia gas is given by 44.3 minus 23.6 exponent of 766.6 over the temperature in degrees K. And the liquid molar volume at 0 C may be taken as 31 cubic centimeters per mole. Well, this is just, we're asking to calculate the fugacity of a pure liquid under given conditions. We have the formula for that, there it is. And it involves these three factors. One of them, the big one, is the vapor pressure, and it's modified by two factors. One of them is this fugacity coefficient for the saturated vapor at the temperature of interest. And this one is called the pointing factor, this last one. This is the pointing factor that will account for the pressure effect, and it looks like we're definitely going to have one because we've got a very high pressure here. So we proceed with it. From Antoine's equation, we get the vapor pressure for liquid ammonia at 0 C is 4.258 bar. And now to get this guy, we expect that it's going to be not very different from 1. But we have the information that allows us to calculate it. We can get the second variable coefficient at the temperature of interest here is minus 346.3 cubic centimeters per mole. So we have an expression for the fugacity of that pure gas. This is the saturation pressure, so that's why the S is exponential of that second variable coefficient times the vapor pressure over RT. And indeed, it works out to be pretty close to 1.937. So then at 150 bar, we'll be interested in calculating this pointing factor. But I put it in the total expression, so I've got, here's my phi S, there's my vapor pressure, and when I plug in the numbers for the pointing factor, I end up, I didn't calculate that separately, but it's rather significantly different than 1, giving me a final fugacity here of 4.87 bar. Okay. So number 5, we got mixtures of nitrogen and methane at 200 K. Second variable coefficients are given here, both the pure component coefficients and the cross coefficient. And you're asked to evaluate the partial molar volume and the fugacity of methane in a mixture of 60 mole% methane, 40 mole% nitrogen at 200 K and 30 bar. So we have expressions for the partial molar volumes for this. The assumption here is that we can describe this using the Pitzer formula. And here it is RT over P, this is right in your notes, plus the second variable coefficient for the component 2, plus the opposite mole fraction squared times this delta 1, 2, which is twice the cross coefficient minus the pure component variable coefficients. And it has a value of 20.6 cubic centimeters per mole. So now it's just a matter of plugging in. I get the partial molar volume of component 2 is 452.6 cubic centimeters per mole. And it's, I can now get at the fugacity coefficient for that component, and the idea of getting to the fugacity itself, which is calculated this way. But I've got expressions, you've got them in your notes here, log of the fugacity coefficient of a component 2 in a mixture, hence the hat over it, P over RT times B22 plus the square of the second of the other mole fraction times my, it should be a delta 1,2 typo. So when I plug in those numbers, I end up with minus 0.1835, and exponentiating, I get a V2 of 0.832, then it's a matter of plugging that back in, and I end up with a result of about 15 bar for my fugacity. Any question about this one? Now we come to the important last problem here. At minus 100 degrees C, a gaseous mixture of 1 mole contains 1 mole percent of carbon dioxide gas and 99 mole percent hydrogen. The mixture is compressed isothermally to 60 bar, and you're asked to determine if any of the carbon dioxide precipitates, and if so, how much. And then you're given information describing the system. At minus 100 degrees C, the sublimation pressure here is very low, 0.1392 bar. And the molar volume of the solid is 27.6 cubic centimeters per mole. In addition, we've got the virial coefficients, both the pure component and cross-virial coefficient for the carbon dioxide hydrogen mixture at the relevant temperature. Okay, so here's the deal. We've got this gas mixture, and this is 99% and 1% here to begin with. Under these conditions, and you're asked if any solid precipitates. And of course, the first thing you need to realize is that it will precipitate if the fugacity of the carbon dioxide in the gas is higher than the fugacity of pure solid CO2. Because it's the difference in those fugacities, the driving force for the precipitation process. Does everyone get that? That's the most important thing to get, because if you don't get that, then you can't go further. So we need to calculate both of these fugacities. Fugacity of the component in the gas, that's similar to what we've done before in an earlier problem. It's formulated this way as fugacity coefficient times the mole fraction times the pressure. We just proceed to calculate the numbers we need for that and end up finally with fugacity in the gas of 0.492 bar. Any question about that? Then the other issue is to get the fugacity of the pure solid. We've also done that sort of a problem in a previous problem in this set. So that's just a matter again of sublimation pressure modified possibly by these other two factors, the fugacity coefficient of the pure saturated carbon dioxide at that temperature, and the Poynting factor. And it's rather high pressure. I think it said, what we got here, 60 bar, so we expect that's going to be significant. And when we do the calculations, we end up with a fugacity for the pure solid, 0.156. So that's to be compared with what we calculated for, where have I got it? With the 0.429 for the gas. So this is clearly larger. Fugacity in the gas here is larger than that of the pure solid. So we expect that precipitation will occur. Yeah.
Yeah, so you approximated the coefficient as 1 in this case, but in the previous problem, a couple of problems ago, you didn't approximate it. How do you know when you can approximate as 1 and when to not?
Well, the guess here is that the pressure that we're dealing with here is 0.13 something bar, so it's pretty darn good guess. When you get that low a pressure, essentially everything's an ideal gas. However, you're making a good point, because we could calculate. We have the information we need to calculate. Did anyone do it?
Yeah.
What did you get?
Like 0.998.
There you go.
Basically 1.
Yeah. So we've got the answer to our question, and now what is the first question, and now what's going to happen is it's going to precipitate until those fugacities equal out. And what that means is that the fugacity in the gas mixture is going to drop down to the value associated with our pure solid CO2 0.156. And what is changing as the gas is precipitating out is the mole fraction that's left in the gas. So we know that it's going to have to equalize out at 0.156. The variable here is the mole fraction of this component, of the component in the gas. So let's write this out, and here's the total expression. And we've got this y1 squared, that is the mole fraction of the hydrogen squared. It starts, the highest value you can have is 0.99, and we're going to square that, that's 0.999 something, 0.99 something also. And so we expect that as it gets lower, this is going to be certainly negligibly different from 1. So that makes it simpler, we just knock that out as 1. And now I can solve this quickly. I get a y2 value here. The mole fraction will drop from 0.01 down to 0.00353 to make the fugacities equal. And now it asks how much precipitated, so this is another 310 problem, just a material balance. So I take a basis of 1 mole of the original gas mixture and let X be the fraction precipitated, so this is going to be written out as the original moles of CO2 in the gas minus the final moles of CO2 in the gas divided by the original moles of CO2 in the gas. When I formulate that ratio, here it is, in terms of X that I've defined, and I end up with about 65% precipitating. Any question about this?
Can you explain why the fugacity of the solid isn't the same as the sublimation pressure?
Well, it's because we're at such a high pressure that the pointing factor is significantly different than 1.
So, okay, so at equilibrium, the saturation pressure of, if it were pure carbon dioxide, the saturation pressure, the fugacity at equilibrium would be 0.1, the sublimation pressure. But since it's in a mixture with hydrogen,
Fugacity is equal to the sublimation pressure, and that is in turn determined by whatever the temperature is.
yeah, you said the sublimation pressure was 0.1932.
Something like that.
Okay, so it's different than the fugacity of the solid we have right now.
Right.
And I'm wondering if that's because the carbon dioxide is in
It's because of the
a.
pointing factor. It's because of the high pressure, as expressed by the pointing factor.
It's not because of the hydrogen. If it were pure CO2, would the fugacity of at equilibrium be 0.139 the sublimation pressure?
Yeah, but I can only apply a different pressure by having another gas present.
Yeah, that was my
Yeah.
question.
So your question about a pure, it's an inoperable question, because I have to have another gas there in order to be able to exert that higher pressure.
Yeah, sure.
Okay?
If you gave us a pure gas,
Well, then
And-
that would be the end of the story.